everybody. Today we are going to start a new module in 11th week, and we are going to now look at some of the important applications of supramolecular chemistry. And the next few lectures we are going to focus on supramolecular catalysis, particularly with respect to supramolecular reaction vessels, and we look at supramolecular photochemical reactions. So, we look at some very interesting aspects of supramolecular chemistry, where we now try to understand whether certain chemical reactions between say different substrates which give rise to the desired products are actually affected by the conditions of the reaction. For example, the concentration of the reactants, the concentration of the catalyst, the nature of the solvent, the temperature, and other factors which control the yields of the reaction product. So, what was thought by the scientists is that can we actually change the conditions such that we can promote these chemical reactions to happen in a more facile way, where we can have altered pathways for chemical reactions via altered transition states, and these transition states can be stabilized, and once these are stabilized with a relatively lower activation barrier, the reaction rates will strongly influence the outcome of the reaction and the yield of the products. And also whether these reactions can be done in supramolecular vessels which are made up from metal ligand complexes, so as to confine the reactants within these cages which are formed from the self-assembled nanostructures involving metal ligand complexes, and promote and accelerate the rate of the reaction such that this supramolecular cage essentially functions as a catalyst, and there exist different non-covalent interactions between this supramolecular cage with the starting materials that can influence the reaction outcome, and almost giving very high rate enhancement similar to that achieved in that of enzymes, and thus this became a very interesting area which we refer to as supramolecular catalysis, which is mediated by, for example, supramolecular reaction vessels. So, with this background in mind, we would like to now suggest that we can now take either self-assembled coordination cages, or we can take also self-assembled organic capsules which are actually held by non-covalent interactions, and they form a molecular barrel like structure into which we can now put these reactants and perform the reaction. And one such example we have seen is in case of cyclodextrins, which have this hydrophobic cavity and the hydrophilic exterior, where you can have the chemical reactions, and also some of these function as enzyme mimics. So, we can have these coordination cages to perform homogeneous catalytic reactions via supramolecular reaction vessels. And what is more important is the control of the cavity environment and the selectivity in terms of binding of the reactants, and the binding selectivity is relatively easily achieved as small changes in the geometries of the building blocks can lead to large changes, in the overall structure and properties of such hollow polyhedral coordination cages. So we have these hollow entities which are which are built up of polyhedral units and consisting of metal ligand bonds, which we have already studied is a process of strict self assembly. And we also know that, as we have mentioned, that the reaction medium affects the formation of the products depending upon the binding of the reactants in subtle ways, and therefore it is very important to use these kind of coordination cages to achieve organic transformations. The very limiting step here is that once the product is formed, it also has got a tendency to bind with the supramolecular cage. Therefore, it is very important to enhance the process of removal of the product from the coordination cage once it is formed, so that the equilibrium can be shifted towards the right hand side. So, this product inhibition is often encountered in this process of supramolecular catalysis, and there we have to engineer ways that once the product is formed inside the supramolecular cage, it must be removed easily in a facile way, so that more of the reactants can react to give rise to the product, and that will overall accelerate the rate of the reaction and also enhance the yields of the process. And therefore, when we perform these kind of reactions inside supramolecular cages, what is more important is the stabilization of the transition state to achieve a geometry that is closely related to that of the product. And this is very important, that the reactants have now been almost pre-organized into a situation that they are able to perform the necessary reaction by changes in the electron density distribution and form the product in a facile way. So, the geometry of the product is very closely related to the transition state via which the product formation takes place. And also, if we are able to have the self assembled coordination cages with the help of chiral ligands, then these also give us the necessary asymmetric micro environment for promoting stereoselective reactions via non-covalent interactions between the supramolecular cage with the starting materials. So, if the supramolecular cages have chiral ligands, then this gives an asymmetric microenvironment for promoting stereoselective reactions via pure non-covalent interactions, NCIs. So, in order to understand the kinetics and the overall thermodynamics of the process of substrate reaction to give you the product via a particular supramolecular cage, we have the following reactions. So, we have the substrate, then we have the host, which are in equilibrium as governed by the rate constant for the forward reaction as K1 and that for the backward reaction, where the substrate you see is a part of the host, and then we have the K catalyst, we can also write it as K2, which can give rise to the product followed by the release of the product into the bulk solution and the host getting empty. So, for the release of the product, K3 must be greater than K minus 3, and the first step must be a fast and reversible step. So, the first step is such that the substrate must be able to bound to the supramolecular cage, but then if this process is not favorable, it should also be able to disengage, and therefore, the step should be reversible. And the second step, which is the catalytic step, where actually the transformation of the substrate to the products takes place, is actually the rate limiting step. So, it is in this step that the conversion from the to the products takes place, and we can actually represent this by the Gibbs free energy G as a function of the reaction coordinate, where we can show that we have got the substrate, then we have got the substrate inside the host, then we have got the product inside the host, and finally we have got the product, and this takes place by a series of steps to give you the final reaction product. And this is the catalysis step. So, this is a transition state which is catalyzed. This is the delta G for the catalytic step, and if we are to take the uncatalyzed pathway, then a conversion from the substrate to the product happens, where we can, this is a transition state for the uncatalyzed pathway, this is the delta G dagger for the uncatalyzed pathway, and this now gives us the delta G difference for the two transition states. So, the transition state for the uncatalyzed reaction, the transition state for the catalyzed reaction is here, and this gives us the delta G transition state. And compared to the starting material, the intermediates which are formed are slightly stabilized. They are also slightly stabilized, and finally, the product is much more stable compared to the starting material, and this stability difference is referred to as delta G0 En, where this tells you the small change in Gibbs free energy accompanying the formation of the substrate with the host. So, overall this is the profile of the reaction. So, when you have a catalyzed step which involves supramolecular catalysis, the initial step involves the binding of the substrate with the host, and now the reaction takes place, and this is the activation energy. So, right away you can see that there is a lowering of the activation energy when you have got the supramolecular cavity or the supramolecular cage which actually binds to the host. The chemical reaction takes place, and then the products are slightly more stable compared to the host with the substrate, and finally leading to the formation of the product. So, it is important to keep in mind that that the transition state lowering takes place for a reaction which takes place by the supramolecular cage. So, we can actually take a example where we have, for example, we can represent this, we can have a tetrahedral cage here. This is a tetrahedral cage. We have this as K1, K minus 1, where now the substrate goes inside, the cage. This is K2, which is the catalytic step, and then we have the product formation here, and then K3 K minus 3 where the product is released into the bulk. And it is also important to keep in mind that the product must be not strongly bound with the supramolecular cage. The product must be weakly bound in comparison to the substrate, otherwise product inhibition takes place. So, and then now we can also account for the extraordinary reactivities because of the transition state for the catalyzed step being stabilized in comparison to the transition state for the uncatalyzed step, which leads to the fissile formation of the products. Now, with this background in mind, what scientists now started designing different kind of supramolecular cages, where they felt that this supramolecular cage can give the necessary environment for the organic transformations to take place. So, to start with, first they thought about metal free supramolecular assemblies, where for example they first looked at crown ether, and crown ether is weakly hydrophobic and therefore and hence difficult to encapsulate non-polar guests. So, that was a limiting factor with crown ethers, and the next choice was cyclodextrins, which proved to be very successful in this regard. And then people started looking at cucurbituryls, which are having this kind of molecular barrel like arrangement, which are made up of purely organic components. We call this a molecular barrel, which can actually promote catalysis inside the molecular barrel. But the problem with cucurbituryls was that there is a high affinity for the cavity. There is a high affinity for the cavity by the product. And the catalytic turnover, which is a measure of the efficiency of the catalysis process, the catalytic turnover is low. So, it is also important that when you perform supramolecular catalysis, you actually have high turnover numbers. The catalytic efficiency is high. You are able to repeat this procedure a large number of times without the catalyst undergoing degradation or decomposition. So, catalytic turnover is low, and also the product inhibition is more because it binds with the cucurbituryls strongly. So, what was thought is that, keeping in mind that some systems are positive and some are negative, in case of organic moieties, people started designing metal based SCs, which are called as supramolecular cages, and they help to overcome the problem of product binding inside the cavity. So, they overcome the problem of product binding inside the cavity So it is possible to now remove the products very easily, and also strong substrate binding inside the cavity. As you know that the first step which we saw is a reversible step. It should be able to fast bind, but it should also be able to disengage. So reversibility is maintained. So the substrate should not strongly bind with the supramolecular cage, otherwise it will be difficult to perform the chemical reaction. So the strong substrate binding inside the cavity and the problem of product binding, once it is formed, these two were overcome if we can go for metal based supramolecular cages. So and this has been also done keeping in mind that the metal ligand bonds are labile, and as we have already seen, these allow for the formation of thermodynamically controlled assemblies. So these cages result in large self-assembled structures, and these are the thermodynamically controlled assemblies, and their formation is rapid and specific. So with this in mind, the first discovery of this kind of a nano cage was again a case of serendipitous discovery by Franck, who synthesized first the magnesium salt of condensed diethyl malonate. So let us take this diethyl malonate, we treat it with methyl magnesium iodide phosgene and work it up with a base and water. It leads to the formation of magnesium 2 plus whole 4, ammonium whole 4, and then it gives rise to this is the delocalized negative charge, this is the delocalized negative charge which is present here, and this is 6 such units. So this is minus 12, this is 8 plus 4, this is 12. So total it is electrically neutral. And now we see these are this has got topicity 2, this is a ditopic ligand, this is one binding domain, this is the other binding domain, and initially it was thought, looking at this composition, that magnesium is octahedrally coordinated with 6 such units, but when the crystal structure was done, then it was revealed that the magnesium exists in a tetrahedral environment. So this being a ditopic ligand, we can write it as follows. So these are the this is one particular binding site, this is the other binding site, and what it forms is where we have got the 1, 2, 3, 4, 5, 6 edges. The magnesium is present here at the ends of the tetrahedral building block, and then between the two magnesium centers we will have the ditopic ligand. So, the ditopic ligand sits with the corresponding magnesium centers. So, these are the tetrahedral coordination environment which is there around every magnesium atom. So, magnesium exists as distributes the tetrahedral magnesium, and so now you see that there is a cavity inside, and this can be used for encapsulation of molecules. However, the size is small, and therefore it is difficult to do reactions with large substrates, and therefore what was thought is that now large polyhedral cages can be made for effective encapsulation. So, with this background came the pioneering work by Fujita, who developed different cages. Now, the first popular work of Fujita was the octahedral cage, where he made this so this is the octahedron, and then this particular face of the octahedron contains this particular ligand. This is N, and we can now have the coordination with the palladium. Here. So, to start with, we can have palladium sitting here at all the 6 centers, and we have then the 6 ligands which are present here. So, they can be so we have got this 1, 2, 3 and 4. We have got these 4 ligands which are palladium 2 here. So, so this is gives rise to the palladium L4 12 plus 12 nitrate is the counter ion, and then every PD actually is equivalent to so the other 2 sides can be coordinated with nitrogen coming from this particular ligand. So, this particular octahedral cage was now designed. So, the one particular face is represented here. This is referred to as so there are 6 palladiums. So, 6 2s are 12, and there are essentially 4 ligands which are present here, one here, one here, one here and one here. So, this face, this face, this face and then this particular face. Alternate faces have got this ligand backbone. Compared to this, there was another cage which was synthesized by Fujita, which referred to as the square pyramidal page, the square pyramidal cage, in which case he had okay. So, this is the square pyramidal, and so all the 4 faces 1, 2, 3 and 4 they were occupied this by the ligands, and we have the palladium here, palladium here, palladium here, and palladium here. So again we have got this is a square pyramidal cage, but you see that the shape of the cage is very different, and this is a bowl shaped molecule. Okay. So this bowl shaped molecule was developed by Fujita, and then there was another supramolecular cage, the third one. I think we have gone to, so we have 2A and 2B, which were developed by Fujita. Then we go to the another supramolecular tetrahedral cage of the M4L6 type, which was developed by Calder and Raymond. For supramolecular catalysis, this is using gallium 4L6. So this is 3 and total is 12 minus charge. So overall the charge on the supramolecular cage is also very important. In the case of palladium, the overall charge is 12 plus. So the charges are very high. So that means that there are going to be strong electrostatic interactions between the substrate and the supramolecular cage, and so that is going to play a very important role. And once the substrate enters into the cage, the water molecules from inside the cage are going to be released into the bulk. So this process is also favored thermodynamically because there are enthalpy considerations, electrostatics as a very strong binding force, and then entropy factors because water are now released into the bulk. So that increases the entropy of the water molecules and thereby favoring the release of the water molecules into the bulk. So both enthalpy and entropy considerations favor these processes. And L is a ligand which is actually having each ligand is having -4 charge, and so 6 4s are 24 and this is 4 3s are 12. So 12 minus 24 gives it the overall charge of -12. And what is L here? L is 1 5 bis 2 3 dihydroxy benzoyl amino naphthalene. This is my ligand, and let us look at the structure of this ligand. So we have the gallium, so we have the gallium here, and this forms so this is the NH, this is my naphthalene ring, then this is NH, CO, O minus, O minus. So this can coordinate with my gallium here. So you can see that this is overall 12 minus charge. So this is an anionic supramolecular cage, and therefore you can have electrostatically positive species in substrates which can get electrostatically bound inside this particular cavity. So what has been observed is that this particular cavity, which you call as the GA4L6 cage, has been utilized as a molecular container to catalyze the Aza-Cope electrocyclization reactions of allyl ammonium cations. So the Aza-Cope electrocyclization reactions of these positively charged species, these are the ammonium cations, so definitely they will get electrostatically attracted to these gallium GA4L6 supramolecular cages. And what is the advantage of these supramolecular cages is that they are topologically, as you see, they are similar to magnesium cage but have larger cavity. So let us look at this process now as to how this thing takes place. So we have this particular acyclic host, and what happens now inside this particular container. So we now are going to put this molecule inside a container, whatever the cavity size or the cavity space is available to it, and there it will undergo an orientational change where you can see this is how I put it as now. There is a bond rotation, there is now a bond rotation which will now bring these double bonds into close proximity with each other so that they can react with each other. And now we can have the reaction here. So we can have this movement here, we can have this movement here, and we can have this movement. So this will give rise to R2, R3, M and M. This is R1. This is R1. And once this product is again, all this reaction takes place inside the cyclization or this electrocyclization via this pre-organized substrate takes place inside the molecular cavity of this GFOL6, and once this is formed, this product is released, and where this product now is N plus Me R3, R2 and R1. So this is my product, and now we can do the hydrolysis, facile hydrolysis, eliminate the dimethylamine, and it will give the corresponding aldehyde. R1. So this electrocyclization, the Isotop electrocyclization reaction now takes place at very unprecedented rates. Therefore, there is a 854-fold acceleration when this reaction is performed in the supramolecular cage, number 1, and number 2, there is a high turnover for this particular reaction. So this is the power and of doing supramolecular catalysis, that you are able to do certain reactions in bulk which do not take place at very high rates. You can actually achieve very high rates when you actually confine this reaction of this cationic substrate into an anionic supramolecular scaffold, which can pre-organize this particular reacting material into a particular preferred geometry, such that the double bonds come in close proximity with each other because of the limited space. The rearrangement takes place, and then it gives rise to the desired product, which is expelled from the cavity and then can be easily hydrolyzed to give you the corresponding aldehyde, which is the final product. So in the next lecture, we will now look at more examples of supramolecular catalysis and their applications using other supramolecular cages to be functioning as reaction vessels. Thank you.